Okay, so draw these two Lewis structures. Don't worry about these guys. And same thing for 56. Draw these two Lewis structures. Don't worry about these two guys. And for 57, only focus on NO2 minus, which is what, nitrite. And notice you're supposed to draw the Lewis structure, and then you're going to end up with being able to swing lone pair electrons from two different oxygens. So show those two Lewis structures. Those are the resonance structures of NO2 minus. All right. So, any questions about this? We're going to go ahead and skip part 7 and 8. We might come back to it, but I want to go ahead and get to the number crunching part. And your unit exam is going to be next Thursday. I meant to, well, I'll bring it Monday, but I'll have one of those kind of outlines for what your unit exam is going to look like. In fact, I'll probably put that together this weekend and just email it to you so you have it in case you want it. MW stands for molecular weight, and FW stands for formula weight. I kind of mentioned this in lab yesterday, that we are basically going to come up with how much a molecule weighs. Not too bad. We're going to use the periodic table. Got mine handy. Come up with how much a molecule weighs. We said if it's an ionic compound, instead of a molecule, we call it a formula unit. So that's why FW is formula weight. So it's basically the weight for ionic compounds. That's the only difference, and this is for molecular compounds. There's a lot of stuff kind of infused in this unit about the two different types of compounds. So molecular weight is how much a molecule weighs. And like I said, we're going to use the periodic table, and we're just going to add them up. It's not too bad. We're found by adding up together all the average atomic weights of all the atoms in the molecule. Not too bad. Synonyms for molecular weight. Average molecular weight, same thing. Molecular mass, same thing. And then the next slide, formula weight, FW, is for ionic compounds. And I didn't mention, but molecular weight and formula weight, they're both in units of atomic mass units, or AMUs. I'm used to using the symbol for atomic mass units abbreviated as AMUs. I think your textbook uses just the letter U maybe. I'm not sure for AMUs. For instance, on the periodic table, if we pick on carbon, which we do a lot, for the element carbon, the decimal number is 12.01, and that is the average atomic weight of a carbon atom, AMUs or U's. All right, so let's do a couple examples. But before we do that, there is a little bit, and this is more semantics than anything, but out there in the real world, it's possible that they kind of don't make the distinction between molecular weight for molecules and formula weight for ionic compounds. Molecular weight can be a formula weight, but a formula weight is not necessarily a molecular weight. Semantics. Okay, so hydrazine. The formula for hydrazine, it has 2 nitrogens and 4 hydrogens. So we're going to use our periodic table, find nitrogen and find hydrogen, and do a little problem here. Okay, so the decimal number for nitrogen is 14.01. We're going to take 2 times 14.01. The decimal number for hydrogen, and I have a rule of thumb coming up that if it's a light element, the first 4 elements are pretty light, so we go with 3 decimals. So we're going to go 1.008 for hydrogen. There are 4 of them. So the molecular weight for hydrazine is 32.05 AMUs, atomic mass units. Not bad. I like the feel of your calculators. So that was a molecular compound, and we know it's a molecular compound because there's no metal there. So this is an ionic compound. We know this is an ionic compound because calcium is a metal. So the only catch here is to make sure we distribute that 2 through the problem, because remember, when we have parentheses like this and a 2 outside, that means that we have 2 nitrogens and 2 times 3 are 6 oxygens. So that's the only catch there. So we need to look up the decimal number for calcium, 40.08. So we take 1 times 40.08 AMUs, plus 2 times 14.01 AMUs, that's for nitrogen, plus 6 times the decimal number for oxygen, which is 16.00 AMUs. Rounded it to 2 decimals, we got 164.10 AMUs. Pretty straightforward. So on your unit exam on Thursday, I'll probably have one of these. Not too bad. Okay. So, yeah, I didn't want to pile on too bad, so I kind of pared back a little bit. And I have these to look at, but if in your notes for this assignment slide, these will be due Monday also. For both 83 and 84, if you just do the first 2, if you do A and B, that's regular credit. And if you do C and D, that's extra credit. Every place that you feel like you're okay to do extra credit, every extra credit you do, you'll get 10 points. So that's a lot extra credit. Okay, so we'll take a look at those right quick. 83 and 84. They look like this. So 83 says calculate the formula mass for each compound. So what your author's doing is just going generic formula mass, and it could be a molecular weight or formula weight. So formula mass is generic. So you just have to do A and B and in both of them. That's not too bad for normal credit. And then, okay, so I kind of want you to be mulling this over the weekend. So you need to take it up a notch. Okay, so what we just came up with was the weight, the molecular weight or the formula weight of a molecular or ionic compound. I have some recall slides here. I think these are still in your notes. So basically, we can use, I'll show you how we can get there. But we talked about the concept of a mole. So a mole is 6.022 times 10 to the 23rd of anything. That's what a mole is. It's a lot of things, okay? And it's a lot of particles. And the reason a mole comes in handy with regard to chemistry is atoms are very small, molecules are very small, okay? So 1 mole is equal to 6.022 times 10 to the 23rd of anything. And we came up with a couple of conversion factors. So from way back in Unit 1, we talked about taking an equality statement and making it into a conversion factor. So 1 mole is equal to 6.022 times 10 to the 23rd. So we can put 1 mole over 6.022 times 10 to the 23rd anything, or we could put 6.022 times 10 to the 23rd anything over 1 mole. So we're going to use those as conversion factors, or we can use them as conversion factors. So we could switch gears from atoms to molecules now, okay? So it's the concept of a mole holds up with atoms and holds up with molecules. So we come up with these two relationships with regard to molecules. If you have a mole of water molecules, you have 6.022 times 10 to the 23rd water molecules. If that works for you. And we could say the same thing for ionic compounds. 1 mole of formula units is equal to 6.022 times 10 to the 23rd formula units. And we could come up with 2 conversion factors. Remember, the conversion factors are the inverse of each other. All right. Well, a mole is awesome because a mole is 6.022 times 10 to the 23rd of anything. But we said for the elements, there was this important concept for the elements called molar mass. And we said you know the molar mass of any element if you look at the decimal number. The molar mass is grams you need to set aside to get 1 mole. In the case of the elements, 1 mole of atoms of that type of element. The molar mass, grams per 1 mole. And we said for elements, the molar mass was the same thing as that decimal number. For elements, like for carbon, the molar mass for carbon is 12.01 grams per 1 mole of carbon atoms. Well, now that we're talking about compounds, the molar mass for the compounds is the same thing as the weights we talked about this morning. So the molar mass for a molecular compound is the same number as the molecular weight. But units of molar mass are going to be grams per mole. Okay. The molar mass for the ionic compounds we get from the formula weight. Okay. So I'll kind of show you how that works. But once we have the grams per mole of a compound, we can use it just like we did the molar mass for the elements. We use the molar mass for the elements to go back and forth between grams and moles for the elements. We are going to use the molar mass for compounds to go back and forth between grams and moles for compounds. Same thing. Very symmetrical. So we aren't going to use them as a conversion factor yet, but let's just go ahead and do this exercise where we knock out the molar mass, the grams per mole of these two compounds. The first one is a molecular compound. The next one, ammonium chloride, that's one of the exceptions that you're like, oh my goodness, I don't see a metal in there. And there really isn't an obvious metal, but ammonium is NH4+, so that's a cation. That's an ionic compound. So let's knock out the molar masses of these. Now, this first way I'm going to show you is what I call the explicit labeling. This slide right here, I'm not going to expect you to work a molar mass problem like this to come up with the molar mass. But I bet you by this, that in the formula, this formula, we have C2H6. If you have 1 mole of C2H6, does this make sense? 1 mole of those molecules, the fact that the subscript for subscript for C is 2, you have 2 moles of carbon and 6 moles of hydrogen. Okay, that's what the formula says. So in 1 mole of the compound, we could see how much it weighs by taking 2 moles of carbon per 1 mole of compound, C2H6. That next term there is the molar mass for the element carbon. 12.01 grams of carbon per 1 mole of carbon. Notice units of moles of carbon will cancel. We're left with grams of carbon per 1 mole of the compound. So that takes care of how much the grams of carbon there is in 1 mole of C2H6. And then we have to do a similar thing for hydrogen. So there are 6 moles of hydrogen per 1 mole of compound. 1 mole of C2H6. The decimal number for hydrogen is 1.008. So that means there's 1.008 grams of hydrogen per 1 mole of hydrogen. Notice that the moles of hydrogen cancel out and we're left with grams of hydrogen per mole of compound. So now we have grams of carbon plus grams of hydrogen per 1 mole of compound. We just add those two together, or multiply through and add the terms together, rounding it to 2 decimals. You end up with a molar mass of 30.07 grams total per 1 mole of the compound. Now that's a lot of work. The word explicit means you didn't leave anything to the imagination. It means you just clearly wrote where that came from. If I was doing this problem on a test, it would look like this. Okay. Notice that these 2 slides, we get the same number, 30.07 grams per mole, but this is a lot easier. It's the abbreviated way to knock out a molar mass. So of course we still have two terms. The first term represents the mass brought by the carbon. There were two moles of carbon. The molar mass for carbon is 12.01. The second term accounts for the hydrogen, 6.6 times 1.008, still rounded to 2 decimals. So this is what I would do. But one of the things I run into with this topic in chemistry problems is sometimes students don't want to show all of their work. And you'll see on the tests, and usually with homework, I'll say, show all your work to get full credit. So even though you can tap this in your calculator and knock out a molar mass that you can use later on a problem maybe, you have to show this. All right, molar mass of ethane. Well, let's knock out ammonium chloride. Let's use the abbreviated way. So we need to account for the nitrogen, so 1 times 14.01. And then we need to account for the hydrogen, so plus 4 times 1.008. And then we need to account for the chlorine, plus 1 times 35.45. So we tap it in. And the good thing about logic of calculators is, I think order of operations would be fine if you just put it in just like this. You don't even have to use any parentheses, I don't think, because it will multiply first. So rounding it to 2 decimals, it should look like 35.49. So one of the things also in working this abbreviated way or any way is units of molar mass are always going to be grams per mole. So that's pretty important. Sometimes students get the calculation work right, but not the labeling. All right. So this is where I kind of said, like for hydrogen, we were careful to go ahead and carry 3 decimals, like 1.008 for hydrogen. And there's 2 other elements, so helium, lithium, and beryllium. So for the first 4 elements, they're pretty light. And so if we go with 3 decimals, then that actually gives us 4 significant figures to work with. So that's what you should do. All right. One last type of problem, or 2 last types of problem. So now that we talked about the molecular weight and formula weight, and then actually that numerical number we also then use for molar mass for compounds. Now what I want to do is use molar mass, grams per mole for a compound, to go back and forth between grams and moles for compounds. And it looks like this. So I think we ran into brackets before. Anytime you see a problem with a word in brackets, that actually is kind of an optional word, may not be there for other problems. So when it says how many moles of molecules is 1.28 grams of chloroform, it could say how many moles is 1.28 grams of chloroform. And it gives you the formula. So this is, and I think we kind of did it this way before, didn't we? Do you remember this? Where how many moles, so question mark moles, is 1.28 grams. So we're going to go from grams to moles. And do you see, like, if we do, like we just did a little bit ago, if we go ahead and knock out, I usually abbreviate it MM, stands for molar mass, CHCl3. That will be in terms of grams per mole. And actually, we can use the molar mass then to get from grams to moles. That's exactly what we're going to do. So there's almost kind of a front-end problem to knock out the molar mass of chloroform, and then go ahead and work the problem. So it looks like this. The MM, or molar mass, looks like this. So I would use the abbreviated way. We need to account for the carbon, so 1 times 12.01, plus account for the hydrogen, 1 times 1.008, and then account for the chlorine, 3 times 35.45. And then round to 2 decimals. So the molar mass we're going to use in our problem is a whopping, goodness, those chlorines are heavy, 119.37 grams per mole. And we kind of emphasized this when we did a similar problem with elements. Remember that whole G/mole? Don't leave it like that. I kind of call it fluffing it up. For this compound then, we have 119.37 grams per 1 mole. And remember, sometimes we need to use it the flipped version. 1 mole for this compound is 119.37 grams. So when you work it in the problem here in a minute, you're going to choose one of those two. And then I said we're going to start with what we want to convert, which is the grams. So our first term is going to be 128 grams. Now, if you're only working with one species, you probably don't have to put the species being the compound's name. I would put that over 1 though. So now we want grams to cancel. We want to be left with moles, so we're going to be using what? The flipped version of the molar mass, aren't we? So if we go ahead and bring down that second term I wrote, the molar mass of chloroform, notice now, and again, if I was doing this, I would put this over 1. Notice now our units of grams of chloroform cancel. We're left with units of moles of chloroform, which is exactly where we want to be. Hope this is ringing some bells. So the units cancel, and then of course we need to work with the numbers. So if you take 1.28 divided by 119.37, round it to 3 significant figures, because that's what we've talked about earlier in the class, you should get 0.0107. So yeah, the stuff we worked on in Unit 1 is still coming back to haunt us in Unit 3. Because remember, this is important, but it's not significant. Okay, let's do one more. Un más. So we're dealing with a different compound, and in this case, if I were going to diagram this, okay, it says what mass, so I put question mark grams over on the right, is 0.4444 moles of this compound, methane. So again, we can go from moles to grams using the molar mass. So what you're going to see on the next slide is we have to knock out the molar mass of CH4. And that's how we're going to accomplish this. So it's like a front-end problem. So here's the molar mass. We have 1 carbon atom times its molar mass, which is 12.01. To account for the hydrogen, we take 4 times its decimal number, 1.008. We add those together. So the molar mass in 2 decimals is 16.04 grams per mole. Then the first term is going to be the moles we want to convert, that 0.4444 moles over 1. Again, I probably put this over 1. So now we want, this is 16.04 grams per 1 mole. So if we just bring this term down, our moles will cancel, we'll be left with grams, which is perfect. So moles cancel, we're left with units of grams, and I'm liking 4 significant figures. So 4 significant figures gives us 7.128 grams of methane. And that's it. Sometimes problems look so easy when they're done in here. Okay, so a few slides from now, you see this assignment slide. And actually, instead of just 2, there are 4, I think, listed. So I only want you to do the first two problems, 47 and 48. But notice, but wait, there's more. It's kind of like we did earlier. I only want you to do the first two. I know it's a lot of homework, but, and I guess since it's so much homework, I haven't been doing it this semester, but I'm tempted to go ahead and when you turn this in, make it worth more than one homework. Usually when you turn in a bunch of stuff, I just say, oh, that's worth 10 points. But we'll see what I do. And again, you can do the other two, C and D, for extra credit. But notice that, I'll show you what these look like, yeah. They are just like we just worked. They look like 47, 48? Okay. And in your notes, the reason I gave you the formula is because I didn't want you to try to guess what. You need the formula to know how to work this problem. So these are, let's see, calculate the moles. So, and don't let the word molecules throw you off. Basically, you are going from grams to moles here. Moles of molecules. And in this case down here, you are going from moles to grams. But again, you only have to do the first two for regular credit. And so again, just to double check, we're on the same page. So let's see, maybe I'll just go ahead and write them here. So A is carbon tetrafluoride, so that's CF4. Magnesium fluoride is, let's see, magnesium +2, fluorine's a -1, so that must be MgCl2. And nitrogen monoxide is NO. No. Okay. I know we're done early, way early. Or maybe I talked too fast. If I ever talk too fast, let me know.